So thank you so much. So my talk is maybe only loosely on dynamics, but I hope you can enjoy it nevertheless. So I guess I should start by introducing the main concept of this talk, which is Minimality of Hausdorff topological groups. So not very mysterious. So definition. Let's see the group. How a Hausdorff group topology of G is for minimal. Basically, if G admits if there does not exist some tau prime Hausdorff group topology on G is strictly coservant. Yeah, this is like not the way to do it in Germany or Austria. Strictly coservant and that. So, what are some examples of also group topologies that are minimal? Sometimes you say that the group is minimal. You assume the topology and say the group is minimal. So, what are some examples? Let me start with some examples that are not very related to what I will be talking today, but interesting nevertheless. So, for instance, if you take a semi-direct product of R with the multiplicative group of positive reals, right? With the obvious topology. Okay, I'll try. Okay, another example that has a similar flavor is the Asymptotic group. And some generalization. But let me get a bit closer to the kind of groups I will be talking about today. So,
so here it's the minimal topology, the one we're thinking about.
Yes. So what is okay, so to be frank, I don't know many small groups which have this topology. The examples are mostly groups that are really large, right? So what is one of the first ones is like you take the infinite permutation group with the Tichon of with well, no, the spell Tichon of topology basically. So the topology, the identity is generated by at the basis of neighborhoods consisting of the fixed point stabilizers of finite sets. So this is an interesting example of minimality. But actually, you can put some structure here, and the property and still get something that has this topology. For instance, another example is like you take R, the infinite random graphs, then you can consider its homeomophism group as some closed subgroup of S infinity. And okay, so this, so let's say the restriction of this topology, I don't know how to, we call it the standard topology. So the restriction of this is this automorphism group is right, and something similar happens for things like yeah, they're those rather than yeah, and then there's for instance like if you know the Eurison space is like some very homogeneous universal metric space. If you consider the pointwise convergence topology on its isometry group, you also get some minimal topological group. I've done some work on this, but it's a bit far of the main topic of the conference. I will let it be for now. Okay, so now as I mentioned the compact open topology, I'm pretty sure all of you know about this, but it's not that thing to remind you. So let's a compact open on this homeomorphism group. It's the topology. I will call it RCO. Just the one by sets of the form, right? So right where compact and use. Okay, I hope you can read it. Writing is not very good to begin with, and so it just works. Right, and if you have a compatible metric on if D is compatible, is a compatible metric. Okay, this is just the topology of uniform convergence on compact set. Basis. We have sets of the following form. We call generate the topology. There's a basis, and the identity. This is usually the way I tend to think about it. Right? And then, so this was sort of devised to deal with the homeomorphism groups of compact spaces, really. But there's a nice classical result by Arendt's 43, I think, that says that if X is locally compact, okay, Hausdorff locally connected, that's the condition that the history is connected, then this is like a group topology, right? So multiplication and inverse are continuous. Okay. Yeah, so the question then now is like, when is the compact open topology of? Okay, so this applies in particular to manifolds, topological manifolds. And now the question is, when is the compact open topology of the homeomorphism group of a manifold minimal? I should say Hausdorff. Well, maybe not, but for manifolds it is definitely Hausdorff. Okay, so theorem, so this this is dark side and Lin from 2003. That's like M is a one-dimensional manifold, then compact open topology on the homeomorphism group of M minima. Right, right, so this is not too hard, right? But now the question is what happens in higher dimensions. So unfortunately, in higher dimensions, there's a small obstruction. So right, so this is like, I don't know, proposition. It's a bit complicated story because essentially the observation was made by the Marnik in some paper in 91, but then sort of it was, all the information was finally extracted and made explicit in paper by Chan and Garza again. Nice, they write a very nice, very general statement. I think this is 13. Okay, so the environment, if the manifold has boundaries, it's just not hard, it's just an observation. So if the dimension is at least 2, and the manifold is empty, then the compact group topology is not minimal on the homeomorphism group. And this is witnessed by the following. You take the pullback, so you have a restriction map. Pullback of the compact open topology on the interior of the manifold, right? And so you have a restriction map, right? That M2 right, and consider the compact open topology here, and the image here, and it's still Hausdorff, right? Because every time you have a non-trivial element of them, you can detect it here, but it's strictly coarse. Not very hard. Okay, so that's sort of like an obvious abstraction to minimality, right? So okay, so what?
And it's this minimum? Do they prove that this smaller topology is minimum?
No, but yeah, it follows from what they. Well, no, they don't prove that. Okay, I think in some cases I'm not entirely sure if I. Well, okay. What I prove is in some cases, if you don't have boundary, then the topology is minimum. So it would follow that this pullback is. Okay. So yeah, so my work is an attempt to solve the problem in higher dimension, right? I don't give a complete solution, but it's a nice general family of examples, right? So unfortunately, I have to restrict the category of manifolds I'm working with. So I move to differentiable manifolds, right? So the first thing I prove, right, is like Let M be a seen and a differentiable manifold. This is what I proved dimensional is. Different from 3. So this is mine. And no boundary. Okay, and let H. It is a group of diffeomorphisms that is large enough. Right? So, yeah, group where it's sandwiched between two things. Notice that I show this canonical notation. Right. If then the restriction of the compact open topology to H minimum. Okay. So what is this? So this is like a very well. It's a group of diffeomorphisms that are isotopic to the identity, smoothly isotopic to the identity, to an isotopy that is compactly supported. Identity to a compactly supported. All right. Yeah, no, sorry, I forgot. Okay. Okay. I'm really sorry, I forgot some condition, which is kind of annoying. The condition is that for all embedded a closed ball of maximal dimensions here. Sort of this is you can see this as some subgroup of the morphism group. The compactly supported diffeomorphism of this thing. Right, so this has to be contained in H. Right. Unfortunately, it doesn't seem to quite follow from, because then you cannot always isotope something supported on a ball to the identity. This whole research program of finding exactly for which dimensions that is true. Okay, so in particular, compact open topology and the full diffeomorphism is minimum. Okay, so this is well, it's a bit disappointing, right? Because the compact open topology, or I don't know, weak C0 topology, is really not something that is designed for diffeomorphism groups. It's designed for homeomophism groups. Like diffeomorphism groups have other finer topologies that make more sense to consider, right? And well, fortunately, minimality is something that sort of goes up from dense subgroups, and in many cases, the diffeomorphism group is dense or close to being dense in the homeomorphism group. So this is like another proposition
2021, I think it is, right? So let tau be a topological group, H dense subgroup of G. Then if the topology, the restriction of the topology to H is minimal, then tau is minimal. In fact, the result says that if you add here some condition, you can get an even only if not worth getting into details, right? Okay, so what do we know about the density of diffeos in homeos? It is actually a very complicated problem. Okay, so the most the first thing is that in small dimensions you can always approximate uniformly homeomorphism by a diffeomorphism. So to avoid some technicalities, I'm going to restrict now to those manifolds. So this is a theorem of Munkres. Right, if dimension of M is less or equal than 3, then let's say M closed. Right, in the compact open, well, in the uniform convergence. This dimension 3. Dimension 4 seems to be, as far as I've heard, like a completely unknown or almost completely unknown. And in dimension 5, okay, this is a theorem of Miller, but okay, this is from I think 14. Okay, so, but he's sort of building on some work that was done in the 70s by Munkres again, Bing and Connell. They stated the results basically for Rn, right? And so you can from their results you can extract some very nice characterization. So if let's say dimension of M, again, this is like a differentiable manifold. If dimension of M is at least 5, let's say again, enclosed, then basically, what's the result? You can, okay. So not all, in general, not all homeomorphisms can be approximated by diffeomorphisms, but basically whether they can be approximated or not depends on their isotopy class. So, right, so an element here, an element in homeo can be approximated by a diffeomorphism, uniformly by diffeomorphisms, if and only if they are isotopic. F is isotopic to a diffeo. Right, and so in particular, like everything that's isotopic to the identity. So it's plenty of stuff. Okay, so using this, you can extract some corollary from the previous thing. Right, so M closed, in reality, it is not necessary. Maybe just, right, but I don't want to get into the implications. Closed infinity manifold, right? Okay, so if the dimension of them is different now from 3 and 4, now the 4 drops out. Even more annoying. So, okay, then for all H that is sort of sandwiched between homeo0 and homeo, restriction of the compact open topology to H. This is not an, as you see, the second result is slightly weaker. So this is not like it's not a corollary of all of this on the nose. But okay, if you get a bit into the proof of the theorem of theorem 1, and sort of you can see that it's, this is enough to prove this corollary, right?
And here you don't need the condition of the ball.
What condition? Sorry.
Ball embedded.
No, because no, you don't. There's no condition on the balls here. I guess so. The thing is, in homeo, right? It's not true in diffeo, but in homeo, if something is supported on a ball, like I stop it to the identity. So no, you don't. Okay, so
and sorry, one thing. And this homeo 0 is it compactly supported or all?
No. It's everything.
Okay.
Yeah. Right in such a way that. No, it's a full.
Right.
Okay, so okay, so I wanted to mention also this is sort of one side of the story, but there's another side. There are other results by other people that complement these results here. Okay, so let me give you a definition. This is a theorem. So topological group has automatic continuity if for all, this is a group for all for all group homomorphism, there's no E here. Phi from G to H, where H itself has some topology, and H is a separable topological group. Right, so you pick any group homomorphism, and it turns out that this is magically continuous, so it's automatically continuous. P is continuous. So many things have been proven by now to satisfy automatic continuity, but in particular, there's something that satisfies automatic continuity that is precisely what we need, which is so this is a theorem of Mann from 2016, which also it's based. Some of the ideas are already found in work by Rosendahl. Proves the result for two-dimensional manifolds. So, and the result is that if M is a closed topological manifold, then then let's say homeo. Okay, then let's say any group between homeo 0, was that before, any group, any subgroup of homeo M, containing the one isotopic to the identity, has the automatic continuity with the compact open topology. So H has okay, so I don't know, a bit of an overkill, so many variations of the same, but so if you combine corollary 1 with this result, you get something quite strong. So for H as in for H and M, let's say, as in corollary 1, the restriction of the compact open topology to H is the unique separable Hausdorff group topology on H, right? And in particular, if you restrict to homeo 0, because homeo 0 is simple, so you get that any, so in particular, you have, again, this is a group homomorphism with no further information, right? From homeo 0 of M to some H separable, then either I is trivial or I is homeomorphic embedding, which is basically as topologically rigid as you can possibly get. Okay, I have 5 minutes. Oh God. So maybe I can say a few words about the proof. So okay, so the first thing you prove. So the proof involves quite a few things, some of them a bit unexpected. So I don't know, sketch. So the first thing you prove is, so you take, so you have some M, as in theorem 1, right? And then take, for the sake of contradiction, some tau containing the compact open topology, or well, the restriction to this group H. Hausdorff topology. Right. Okay, so the first thing you do is you show that for all this is, I'm going to write for all neighborhood of the identity in tau, for all balls, for all D, D1, R balls, there exists some element in this neighborhood which sends the first ball to something which has intersection with everything else. This is something you have to, not really that hard. So no matter how small your neighborhood is, because you are assuming that the topology is discretely coarser than the compact open topology. So you can always find, given any ball, you can and given any sort of like any finite family of other balls, you can always find something that sort of sends the first ball to something that crosses all of the other balls. It's a bit of everywhere. Of course, you cannot control how thick the image is going to be or anything like that. There's no preservation of measure, nothing, but at least you can get it to be sort of sufficiently dense somewhere, right? And the second thing is like you can use this to prove lemma 2, prove that for all there exists some embedded so let's say that the dimension of M is M. There's an embedded M minus 1 dimensional complex, right? Such that some sort of stabilizer, some sort of pointwise stabilizer of this thing. Is contained in here, right? So basically, you pick some neighborhood. This neighborhood is going to contain some because it's the topology is coarser. It's going to contain some neighborhood of this compact open topology, right? Let's say this is K. And you pick some ball that is very close to, has diameter, let's say, epsilon. And you know by the previous lemma, you know that you can send this ball, there exists some G, such that I don't know how to draw this. So that the image of this D is somehow, I'm not going to say epsilon dense in K, but maybe like some fraction of epsilon dense in K, right? And you can use that to find some spine here, some n minus 1 dimensional spine inside here, to which you can sort of deformation retract the complement of this ball, right? By moving things less than epsilon. And you can use that to prove that the stabilizer of that sort of spine, I don't know, something I should have picked some colors. It's something like this. The stabilizer of that spine is in your neighborhood, right? Yeah. Oh, right. Yes, of course. Thank you. Okay, I'm too much in a hurry to explain this properly, but the point is like once you have reached this stage, this is very good because now you can focus your attention on the action of our group H into a collection of like sort of lower dimensional data, right? Which is much easier to understand than the whole action on the action on the whole space, right? And then okay, I don't have really time to say much, but there are two things. You do some induction on the dimension to prove this result, which is a bit strange to say because I said before that dimension 3 falls out. But the dimension 3 falls out just at the moment of starting the induction. Like if you have an embedded, if you're working in a 4 manifold and you have an embedded 3 manifold, you can use the fact that the 3 manifolds in a 4 manifold to sort of kickstart the induction. And and then you can use that to prove that basically whenever you have a lower dimensional disk in your manifold, and whenever you have a neighborhood of the identity, you have elements in this neighborhood that are supported in this strictly lower dimensional, in some neighborhood of this strictly lower dimensional disk. You don't know how small this neighborhood is, and this is part of the trick. And then the point is like, okay, and with this I will finish because I'm very over time. So suppose that let's say I have some curve alpha, right? And then I have some element that does something to alpha, right? Or I have, to be more clear, let's say that I have some other curve. I have some alpha, I have some beta, and I do something to beta, right? Maybe something like this, right? Right, so this is G times beta, right? And then the idea is that I can reproduce what G is doing to beta using some control product of two things, of things in the stabilizer of alpha and things that push, okay, that in this case push points along arcs, right? So I could, so to reproduce what G has done to beta here, I could first push it along some, use some elements supported in some very narrow, in some neighborhood of some very narrow neighborhood of some arc here, maybe even doing some backtracking, it doesn't really matter, right? So that to get something like this. And then once I've done this, I could further multiply by another thing, and I could find this in any neighborhood, even in some root of the neighborhood I'm interested in. I could do something similar here, and this could be extremely thin, but it doesn't matter because at the end, using a single element from the stabilizer of alpha, I can sort of open this whole thing, right? And obtain like the act, you know, so that I have and do what G is doing, right? And this allows us to write G as a very controlled product of those two kinds of elements, right? And in dimension 2, this is sort of intuitively obvious why you can do these things. In higher dimensions, you need some tools, right? And one of the tools is like there's this whole theory I didn't know about of stable mappings. You know, when you have a differentiable map and you perturb it slightly in the Whitney topology, you know, in some neighborhood of the Whitney topology, right? You can sort of simulate that perturbation multiplying by some diffeomorphism of the domain and some diffeomorphism of the codomain, right? And I'm using the fact that immersions that are self-transverse satisfy that property, and I'm using some sort of variant of Morse theory to get decomposed isotopes as this sort of slice move along lower dimensional. I'm very much over time. Thank you for listening to me.
Thank you.